The project, titled AI-Driven Gesture Recognition Using Wi-Fi-Enabled IoT Devices for Smart Environment, is led by Zunaira Khan and Waji-ul Hassan under the supervision of Dr. Omer Chugtai. Now, we'll show you an animated theme video of our final year project to give you a clear idea of how it works. When we analyze or measure a signal, the most important thing we observe is the change, not just the signal itself, but how it behaves over time. This change holds valuable information. In gesture recognition using wireless signals, a simple movement, like raising a hand, causes subtle variations in the signal. These changes are captured as data, showing how the signal reacts to motion. Machine learning models are trained to recognize these specific patterns of change. By learning how different gestures cause different signal variations, the model can accurately identify the gesture being performed. The objective of the project is to detect and recognize human gestures by analyzing distortions in Wi-Fi signals during handshakes or other movements. These signal changes, captured as channel state information, CSI, help identify specific gestures like thumbs down, no, or help. The real-world problem and motivation behind this project is traditional gesture recognition methods using cameras or wearables raise privacy concerns, depend on lighting conditions, and can be costly or uncomfortable. Our motivation is to develop a low-cost, privacy-friendly solution by leveraging existing Wi-Fi signals, eliminating the need for additional sensors or specialized hardware. Now we read the system architecture. The system architecture consists of a Wi-Fi router that emits signals, which are affected by human movements. An IoT device captures the resulting CSI data, which is then processed by an AI unit to recognize gestures and trigger appropriate actions in smart home devices. Next slide represent the hardware and software components of this project. The system uses a Wi-Fi router to detect signal fluctuations caused by human gestures, while a Raspberry Pi 4B serves as the edge device for collecting and processing this data. On the software side, MATLAB is used for signal processing and feature extraction, and a convolutional neural network CNN model is employed for gesture classification. In next slides, we show a flowchart of CSI data processing and CSI gesture classification. On a Raspberry Pi 4B using Nexmon CSI, the process begins by enabling monitor mode to allow passive capture of Wi-Fi signals. CSI, channel state information, packets are then captured and extracted from the binary files. Finally, the extracted data is analyzed and visualized using MATLAB for deeper wireless signal insights. The CSI data is pre-processed and formatted, then used to train a CNN model. After training, the model's accuracy is evaluated to classify gestures effectively. In next slides, we see about the comparative model accuracy. The SignFi dataset, which captures CSI data during hand gestures, was used for initial testing and model validation, achieving 96.01% accuracy with a CNN model. After optimizing pre-processing and refining the neural network architecture, our improved model reached 98.28% accuracy, demonstrating its robustness and laying the foundation for future real-world deployment and custom gesture recognition. Next slide, we see some practical application of the project. In real-life gesture-based control systems, simple hand movements can perform smart actions. For example, swiping left turns off the lights, a hand wave increases fan speed, and a circular motion plays or pauses music. This makes device control more intuitive and touch-free. Nexmon tools and technically challenges of the project is Nexmon is an open-source tool that modifies Wi-Fi firmware to capture channel state information CSI data. In this project, it enables real-time CSI collection on a Raspberry Pi to recognize human gestures, allowing non-intrusive control of smart devices through Wi-Fi signal variations. Using Nexmon and enabling monitor mode presents several technical challenges, including a complex compilation process, device compatibility issues, and the need for driver and firmware modifications. Additionally, there is often a lack of debugging support, making it harder to troubleshoot and optimize the system effectively. Next slides, we show some gestures of the project. The gestures used for controlling smart home devices include a handshake, thumbs down, and gestures for no and help. These hand movements are detected through CSI data and enable intuitive interaction with the system. Next slides, we show CSI visualization of the project. The x-axis represents the packet number, illustrating how channel state information, CSI, evolves over time, packet by packet. The y-axis corresponds to the subcarrier index, showing the frequency behavior across different subcarriers, providing insights into how the signal varies across both time and frequency. At the end, we show the conclusion of the project. We developed a non-intrusive gesture recognition system using Wi-Fi-enabled IoT devices and deep learning to classify gestures from CSI data. By leveraging Raspberry Pi and Nexmon, we enabled real-time smart home control without relying on cameras or wearables, enhancing privacy and comfort while laying the groundwork for future improvements and custom applications. Some practical clips of the project. During a handshake between the Wi-Fi router and the Raspberry Pi, human movement causes distortions in the Wi-Fi signals, which are reflected in the CSI data. Similar distortions occur with other gestures, like a thumbs down, a no gesture, or a help gesture, each creating unique patterns in the CSI that can be analyzed for recognition.